So you want to create a universe? Well, there are good reasons for that. Maybe you want to make up a universe where life doesn't have to just stick to planet surfaces, split from the vacuum of space by a thin, delicate atmosphere. Or maybe you're seeking a universe where astronomical distances are shorter, making it easier to explore than ours. Or maybe you just want to make an apple pie from scratch. Good news for you is creating a universe is relatively simple. In theory, it's not much different from building a house. We can break down the process into two parts: the structure of space-time and the universe's matter content. Choosing the structure of space-time is kind of like deciding how many rooms your house will have, where the structural beams will go, and if any hallway will allow for time travel. This is the step where we gotta pick stuff like how many dimensions the universe is gonna have, whether it's gonna expand, spin, shrink, or just stay put. And these decisions are super important. They're the ones that'll decide how long your universe is gonna last and even how long intelligent life is gonna be possible. So let's kick things off with the first big decision: the number of spatial dimensions in the universe. We live in a universe with 3 spatial dimensions, but nothing stops us from envisioning a whole different number of dimensions. There's nothing in physics that says the universe has to stick to just 3 space dimensions. But to be honest, I wouldn't mess with that too much if I were you. The different number of spatial dimensions drastically affects how the fundamental forces of nature behave. In 3 dimensions, gravity strictly follows the inverse square law. So, essentially, gravity's pull drops 4-fold if the distance doubles, and it plummets 9-fold if the distance triples. We're always squaring it. With 4 space dimensions, the force would drop off with the cube of the distance. So, doubling the distance now actually would make the gravity force 8 times weaker instead of 4. And interestingly, tripling the distance would actually cut the force by 27 times instead of just 9. So, in a universe with 4 or more space dimensions, gravity would be far too weak to form complex structures like galaxies and star systems. And without star systems for life to emerge, you'd end up with a bland universe with no sweet, sweet churros. And if you didn't want to make things bigger but actually have less spatial dimensions, you could indeed even have star systems. Orbits of planets are possible in a universe that's just 2-dimensional, kind of like a sheet of paper, but it's hard to picture how a living being or anything more complex than a solar system would come together. 3 dimensions of space seem to be the sweet spot, and I'd recommend sticking to just 1 time dimension like ours. With 2 time dimensions, disrupting cause and effect could be possible. No pun intended, but it's hard to predict the effect this would have. So, with the number of dimensions set out of necessity, the next step is to figure out the structure and story of these 3 space and 1 time dimension. The most natural choice seems to be creating a defined space volume, a few billion light years across, then stuffing it with the kinds of matter you want. And that's just like making a static universe. One that never changes, it's always the same old thing. The thing is, if space never changes, that means it doesn't have a beginning. It means there's an infinite amount of time in the universe's past at any point in its history. But everything in the universe has a finite time to exist. Stars burn their fuel, stellar remnants eventually fall into the black holes at the galaxy's center, and even black holes evaporate and vanish over an incredibly long stretch of time. And here I'm going to make a bit of a leap, but stick with me. This means that at any given moment in the universe, the chance of something still being around is 0, because there's infinite time in the past. So, a universe without a defined beginning is kind of like a universe where everything's already ended in an unreachable past. We truly need the universe to not only have a structure in space, but also, importantly, to have a structure in time. In other words, the universe indeed needs a story. And the start of the story is always the same: the Big Bang. A primordial universe, hot, dense, packed with matter. We'll figure out the matter details later. The real choice is at the end of your universe's story, and in the shape that its space will ultimately take on. One possibility is that the universe might be wide open, ruled by the universe's accelerated expansion. In an open universe, space-time is like a curved potato chip, what mathematicians call a saddle shape. Moreover, this universe ends with the accelerated expansion of the universe tearing apart all complex structures in a brutal fashion, an event known as the Big Rip. Another option is the opposite. The universe might be closed up like a sphere. In this universe, the main player is gravity, which after an initial expansion period following the Big Bang, will pull all of space-time back together, setting the stage for another Big Bang. And the third option seems to be where we're currently at, a middle ground where gravity balances out with the universe's expansion. The universe keeps on expanding, but never with enough power to rip everything apart. This universe is slowly cooling off until its own heat death. And here's a good question. What determines which of these three scenarios goes down is how stuff is spread out in the universe. But if we have not put any stuff in it yet, then how can we actually pick a story for the universe before we've got any stuff? The answer is actually quite simple. We utilize dark energy and dark matter. Dark energy is essentially what's making the universe expand, and dark matter is doing the gravity thing just like regular matter, but without doing anything else, at least as far as we know. So what exactly are dark matter and dark energy? All we know is that our universe is mostly made up of these two things. 3/4 of the energy is dark energy. 1/4 is matter. There's 5 times more dark matter than regular matter. And I know all this seems like a blast, but watch out. Because putting more dark energy than what's in our universe would stop galaxies or maybe even stars from forming. Moderation is key. So the trick to creating an interesting universe isn't just having matter, but having matter that can come together to form more complex types of matter, like quarks, which are the fundamental particles that make up neutrons and protons. And neutrons and protons, which in turn make up atom nuclei that are orbited by electrons, which in turn form atoms. And then these atoms form molecules, which are the base of chemistry that brings about the most complicated and funny thing in nature, life. The first choice is in the mass of the particles that make up protons and neutrons, which are the up and down quarks. Protons are essentially made up of 2 up-type quarks and 1 down-type quark, while neutrons consist of 2 down-type quarks and 1 up-type quark. It's just that around here we've got a restriction. These 2 quarks gotta have similar masses, otherwise the quarks might decay inside the atomic nucleus, and that would make atomic nuclei unstable. That means no life in the universe, and there's another restriction involving particle masses. Electrons actually gotta be at least 100 times lighter than protons. Otherwise, stable orbits just don't exist in the context of atomic structures. Without atoms, no chemistry, molecules, or sweet churros. So to be safe, it's wise to make the electrons super light. But don't sweat it, because you can still pick from the other 4 quarks that exist in nature. And what are they good for? Well, when intelligent life pops up in their universe, they might spend a few decades looking for them. It's kind of like a side quest, a pastime for scientists. If you're looking for more entertaining options, you can actually make your whole universe out of super tiny strings. And it's the vibration of these strings that generate particles like quarks and electrons. That being said, to use strings, you're going to need to create 7 additional dimensions, miniature ones, that basically serve as pipes or plumbing for the strings to coil around. And it's the geometric shape of these dimensions that's going to determine the mass and charge of the particles. As long as the electrons and quarks have the right masses, everything's going to be all right. And the final step to creating your own universe is deciding how matter in it is going to behave. This means figuring out how strong the 4 fundamental forces of the universe are. Gravity, the force that pulls matter together and builds cosmic structures. Electromagnetism, the driving force behind chemistry. The strong nuclear force, which keeps the atomic nucleus stable, and the weak nuclear force, which is behind radioactive decay. What matters is the relative intensity of these forces. For instance, if you raise the gravity too high compared to the electromagnetic force, stars are gonna burn through fuel like nobody's business. And their lives are gonna be way too short for life to evolve. On the flip side, if gravity was way weaker, then stars would be a whole lot colder. And stars aren't going to go supernova. In other words, this essentially limits what elements will exist within your universe. In theory, ideally, gravity should be the most feeble force, 10 billion trillion times weaker than electromagnetism. And yeah, that's pretty weak. But gravity makes up for it precisely because there aren't any anti-gravity charges. And by that power having a literally universal scale, you're being pulled in by gravity from everything in the universe all at once. Interestingly, the second weakest force has really got to be electromagnetism. However, it can't be too much of a pushover. The trick is to balance the electromagnetic force with the strong nuclear force. It's the relative intensity of these 2 forces that determines which elements are stable in nature and which elements stars will create through nuclear fusion. If you're dead set on having life in your universe, the trick is balancing these 2 forces so the equation holds true. The energy of a beryllium atom plus a helium atom has indeed got to be essentially equal to the energy of a carbon atom plus a photon. This balance ensures an efficient production of carbon in the universe, a molecule that's just perfect for life. That equality holds in our universe too. If you're feeling even bolder, You could even try using silicon instead of carbon and see if you can get life out of silicon, but I'm not sure if that's possible. There are also a few other tweaks that matter if you care about the universe's lifespan. The value pinpointing the precise strength of the electromagnetic force is the fine structure constant, which in our universe is about 1/137. The electromagnetic force is responsible for the efficiency of a star's nuclear fusion and also plays a big part in how chemical bonds work and what kinds are even possible. Changing this value could have some pretty disastrous consequences. If the fine structure constant was just a tad higher and the electromagnetic force was only 10% stronger, nuclear fusion would be less efficient and stars might not be able to form. A universe like that would pretty much be filled with black holes. And if the constant is just a tad lower, like 10% or less, nuclear fusion is going to be way too efficient. So stars burn through their fuel fast, having much shorter lifespans and giving less time for intelligent life to evolve. Besides, it's crucial that the weak nuclear force is actually weak for real. Neutrons on their own break down into protons through the weak nuclear force. And if the weak nuclear force is strong, the neutrons in the early universe are going to decay into protons really quickly. And this is going to mess with the formation of hydrogen too, the famous deuterium, which is a hydrogen atom with a neutron in its core. And without significant concentrations of deuterium in the stars, they might not be able to produce carbon or other atoms heavier than it. Moreover, the weak force plays a key role in supernovas, which are star explosions that churn out elements heavier than iron. If the strength of the weak force is different, the outcomes of the elements formed in supernovas are going to change. Or maybe supernovas just become flat out impossible. And if you tweak the weak force so much that you make supernovas impossible, well, supernovas kind of birth nebulas, which are the dust clouds that spin up smaller stars, like the sun. So, no supernovas, no nebulas, no smaller stars fit for life. But aside from those 7 or 8 limitations, you can crank the intensity of the fundamental forces to whatever level you like. After all that, we can finally conclude our discussion and end at the beginning with the incredible Big Bang event. In our universe, modern cosmic structures like galaxies, clusters of galaxies, the bunch of supermassive black holes, and all that jazz are a reflection of the density fluctuations in the early universe. If the matter of our primordial universe is evenly spread out, akin to jelly perfectly smeared on a slice of toast, the universe in the future will indeed stay that way. Space dust is going to be evenly dispersed throughout the universe as it expands, and absolutely no kind of structure is going to form. We really need to throw in just a bit of imperfection into the distribution of matter in the early universe to have some truly fascinating stuff happening. And here, we must really tread lightly. If the imperfection rate is too low, very few, if any, galaxies will indeed actually form. And if it's too high, you'll inevitably end up with all the stuff inside black holes. Interestingly, the rate in our universe seems to be just right for a universe that's densely packed with stars, which is a floor rate in uniformity of 1 in 100,000. This basically means that for every 100,000 particles in our primordial universe, one of them is out of place. And now, you've got all the essential info you need to create your own universe. Just follow these simple rules and everything will be perfectly peachy. Unless we forgot something crucial, like the mass of our Higgs boson ending up on the wrong number after the Big Bang. But then you might as well toss the whole universe out and start a new one. Not everything in life can be controlled. Don't y'all find it weird that the whole universe seems to be perfectly tuned to support life as we know it? Drop your thoughts on the comment section below. Thanks a whole bunch and see you all next time.